I hope we can start now. So this is our first day, second lecture. Let's start with some things that I want to first of all discuss with you. And if suppose you get any problem or difficulty, then no, we have just started, Jay. It is a start. I said good morning. That is the start of our class. Okay. So we are in the time, and here we are going to see. First of all, I would like to tell you one fact which happened with me. You might have attended the yesterday's inaugural session, and in that, Nair sir told that, Vinay sir told you that I am from music field also. That's true. So what happened with me? Actually, I am residing in Nasik, and our All India Radio zonal is at Jalgaon, which is nearly 250 kilometers away, nearly from my hometown. And we have a train to reach that All India Radio by 10 o'clock or 10:15 in morning. So it starts early in the morning. That is a passenger, so it takes halts at every stop. One day what happened, I got a assignment on an assignment from the All India Radio, and I had to rush to catch the train, and I was alone at the home. And in those days, mobiles and other telephones were not there. So I had to manage myself alone and without any assistance of these smart gadgets. Then what happened? I almost completed my things, and every time I put on or wear on the shoes. So I started to wear on the shoes, and before that, just 2 seconds, electricity was off completely, and I didn't have the torch with me, and it will be or it would be late if I went over there to take the torch and all. So then, and I am there not that much particular. So in my box, actually, I have some kind of, say, black socks, then navy blue, then we may say green and chocolate, that is dark chocolate color. So such colored socks are there, and this is dark green, bottle green. And I was not having any option to find out the torch and see in the light that, oh, where is the same color socks. And so what I did, I decided something in my mind. I took some socks in my pocket, in my pant pocket, not elsewhere. And immediately I closed the door, lock it, and rush to the railway station. When I put some socks in my pocket, I decided that when I will be bored on the train, then I shall remove the socks from my pocket and see the same color socks, and then I shall put on, and same color socks will be there with me. So the question is, how many socks I had taken in my pocket? That you have to answer. How many socks that are I had taken in my pocket? Good. So yes, Swasti.
5.
Five. Okay. Ishan.
Or maybe I can take all the socks.
All the socks. Very good. So I had the big box. It is containing more than 80 socks. ah. So shall I take 80? Ishan? Okay. Tanish,
Same answer as Swasti. Five socks
5
to
socks.
confirm that you get two of the same color.
Okay. Aditya. Aditya Rajesh.
Five socks, sir.
5 socks. Okay. Now let's see that if I take only one socks, sorry, if I take only one socks, then what will happen? Either it will be black or navy blue or dark green or chocolate. If I take two, then any two colors will come. If I take three, the worst condition is that I may get three colors. Worst condition. If I take four, then the worst condition is that I am getting all four colors. And now when I am going to take five socks, then it is clear that these four colors at the worst condition will be there. And then any one of these as the fifth slot, so socks. So 4 plus 1, it will happen. And then therefore, the minimum number of socks. I didn't actually ask you to take the minimum number of socks, but I had put one condition that I took those socks in my pocket. So those are that implies that the number would be very, very less. And then therefore, I could work like this. Okay. So what we have thought over here, there is a very much simple and attracting principle behind this, and that is known as the pigeonhole principle. Okay, so let's see what is pigeonhole principle first of all. And obviously without proof now, initially we are not going to have the proof. It is also known as Dirichlet's box principle. Dirichlet in the period of 1805 to 1859 actually introduced or gave this theorem. And even if it is quite a simple theorem, but its uses are very vast. It may have some kind of different versions or different statements, but actually pigeonhole states that there are holes for the pigeons. They made some holes in some old buildings or at the top of some buildings or houses where they reside, like their nest or home. And because of that, this idea had come. We don't know what is the correct thing, but we may say that it's okay, it might have happened. Then, as in our earlier, what our simple question, that four colors are there and we need five socks, so that I am going to get one pair of, that is two socks of same color. So here actually very simple idea that if I have say five objects, same kind of objects or whatever it, say we may call them as pebbles, marbles, pearls, whatever it be. And we have four boxes. And I have to put them five objects in those four boxes. Suppose there are four boxes. Now the case is that I can put all five in one, because condition is not given that at least one to be put in one box. So we have some different options. So I can put all five in one, or maybe at the worst or very final ultimate condition that if I put one object in one box, then the fifth remaining object has one of the boxes, say last one, So it contains 2. Then we have to state it formally. Means what is happening? I have 5 objects and I am putting them in 4 boxes. Then one box contains one box contains at least 2 objects. Now here the word at least 2 implies that 2 or more is possible, but at least 2 must be there, because the condition is not that every box should contain 111 or at least 1, and it is not necessary. Just to distribute 5 objects in 4 boxes, then one box contains at least 2, or at the most 5, then not more than 5, because we have only 5 objects. But all objects are coming in one box is not that much vital, but one box contains at least 2 is important. One box contains at least 2, that is important. And so that is nothing but the key idea behind our pigeonhole principle. The principle can be stated in some different ways. So we may say that our pigeonhole principle in first way, that if n plus 1 objects are distributed into n boxes, then at least one box must receive more than one object. If n plus 1 objects are distributed into n boxes, now remember that when we are writing n or n plus 1, then it means that n is a positive integer that is considered. So it is not necessary to state. So basically how we went for 4 colors and 5 soxes. So 5 socks, that is nothing but the n plus 1 objects, 4 plus 1. And 4 colors, that is nothing but 4 boxes. And so one box contains more than one object, or we say that at least 2. Okay, so at least one box. Now here actually in my statement I wrote here at least one box. Why? Because like here suppose 4 boxes are there and 5 objects to be distributed. I may distribute like 2 3, I may distribute like 2 2 1. So here we had put at least one box. More clearly we can have this statement that if more than n objects, more than n objects more than n objects are distributed into n boxes, then at least one box must receive more than one object. So that is what a basic idea of the pigeonhole principle, and it is but obvious and very much easy to understand. Yes, Srinandan, he has raised the hand. What you want to say?
So if it is more than n objects are distributed into n boxes, uh, for the second statement, can we say that at least one box must receive at least the difference between n and the total number of objects?
Yes, that is what the same thing. Not necessarily means, suppose like when there comes 5 and 4, we have 2. So not difference plus 1, I hope. May I right? Am I right? Hmm.
Yes, sir.
So it is not now here that much important to calculate how many objects one box at least receive. It is clear that at least one box must receive more than one object. Okay. Then it's another version is also there. We may call it as pigeonhole principle 2, that for any positive integers n and t, if tn plus 1 or more objects are placed in n boxes, then at least one box, at least one box must receive more than t objects. So it is a next step or additional thing in our pigeonhole principle, that whenever there are tn plus 1 or more objects, tn plus 1 is the lower limit for that, where n and t are positive integers. When we have tn plus 1 or more objects and to be distributed or placed in n boxes, then at least one box must receive more than t objects, because there are n boxes. So again, it is just a parallel statement for our first statement of pigeonhole principle. Then we know what is an average of some given numbers. So we can extend the pigeonhole principle to the average of positive numbers. Like in our second statement, we got Tn. So Tn is nothing but the product of T into N. And suppose if we say that the average of N positive integers is T, then their summation would be NT. So that is a sign to observe. Okay, Jay, you want to ask something?
Yes, sir. I wanted to ask that can we also say that if there are, for example, if x is which is more than n objects are to be placed in n boxes, then at least one box must receive, for example, p is which is more than equal to x minus n.
Hmm, can be. Now, that is very nice idea that earlier, I think Aditya said that. So it is correct to say, now what you can do, you frame the statement, okay, that you are just experiencing that we can state in this way also. You frame and let's see that what is happening by taking some example. Okay, but when we state the difference, that is what the at least, and it is clear that one box should contain like that. Now see, there would be some kind of thing. Say I have 9 objects to be put in 4 boxes. Okay, then I can put those like 2, 2, 2, 3. But 9 minus 5, sorry, 4 is 5. Then the statement, what just you clicked in your mind, that the subtraction one box contains at least 9 minus 4. Then in this example, 9 minus 4, that is 5, is not contained by any box. Why is
Yes.
it so? Because we are not in the condition that how many objects should be placed in any box. And it is also not considered that the box must not be remain vacant or what. And even if you try to now go ahead that putting the condition that each box should contain any object or not, it remains vacant or not. So try to create the statements, make them or support them with the examples. And after that, try to find out some counter examples. Like this is a counter example what we have the in a difference. 9 minus 4 is 5. So the word at least one box must receive more than one object. So here it is followed as 4 boxes, that is n, and here it is more than n. So at least one box. Here all boxes have received more than one object. So the statement of our pigeonhole principle 1 is very much clear. It is correct that we should have some ideas in our mind. Then try to write them in your own words and then try to support them with some examples. And then try to ask a counter question to you own. Why is this so and why not? And if you are ready to support with enormous examples, then you have verified it. But keep one thing in mind that even if I am not getting any counter example, suppose after some hours or days or weeks, you may get a counter example, then you will realize, oh, then it won't work like that. Remember, this is a new topic which is directly introduced here. You may know pigeonhole principle, you might have heard from your elders and from some good videos available in internet or some any other source. But there are also more prerequisites to go ahead to apply the pigeonhole principle. And you are that much lucky to have very big time to get these prerequisites as well as these next things also. I was talking about the average. So our third version of pigeonhole principle may come like this: if the average of n positive integers is t, then at least one of them is greater than or equal to t, and also at least one of them is less than or equal to t. So try to understand the thing. Okay, you may write. I shall give you the notes, no worry. But we should be habitual to write at our own. While writing, it's 2 times reading. So please write it. Okay. Now, let's think for the statement and try to ask one question to your mind, that can integers be replaced by positive numbers? Does it affect the sense? Comment on this,
Yes, sir.
everyone. Yeah, somebody spoke up.
Sir, perhaps this number includes fractions and decimals. So
Good,
it's
good.
appropriate to use positive integers rather than positive numbers.
So you feel that positive integers is more precise.
Yeah, so
Okay, okay, no worry. Mhm. Yes, Vihan started to speak something. Vihan.
Yes, sir. Can you repeat your question?
Okay. So Vihan, just one informal question. You are from Mumbai or what?
Pune.
Pune. Okay. Sorry. Ha. So here integers, I said positive integers. Then if I say positive numbers, then does the meaning remain same? Is the question. Yes, Jay.
Sir, the meaning will not remain same because if you use positive numbers, so that will include decimals and fractions, and so yes, using the word integers will be more appropriate, I think.
Okay, okay. So let's have some. Yes, Ishan, you want to say something?
Yes, if we include positive numbers, we will include rational numbers, irrational numbers, decimals, fractions,
Uh-huh.
square root. So it will be uh, uh, more better to use positive integers rather than
Okay,
positive.
okay. Tanish.
I think that even integers is not the right word because we can't have negative number of anything.
I didn't get what you want to say.
So like instead of integers, I think we should say whole numbers and zero because uh, like positive natural numbers, like just natural numbers and zero, because if we say integers, it also includes negative numbers,
Correct,
which is
but we
-1,
have
-2.
positive before that. Sorry.
Oh yeah,
We
right. I didn't see
ha.
that.
Okay, okay, okay. No worry. Okay.
Sir, so instead
Yeah.
of positive integers, we can also write whole numbers, right?
No, whole numbers include zero. Okay. Whole numbers are non-negative integers. Hmm. Whole numbers are non-negative integers. Non-negative include 0 and greater than 0. Both. That is non-negative. Here we stated positive integers. And now we are at one point, that whether to use positive numbers or not. Earlier I told you that take some examples. Take some examples, work on them, get the meaning, and then try to comment. Yes, somebody has raised the hand. I think Sai Charan. No, somebody has. Yes, Srinandan. Go ahead.
Sir, I think this statement, the third principle, also works for a case where the average is 0, because if you take a group of numbers and it does not include negative integers, for all of them to add up to 0, every
Okay,
single
give
one
me
of
one
them must
example. Give me one
0, 0,
example.
and 0.
Okay, okay. Huh. Then
Then both of the statements are right, because they are equal, and one of them is at least equal, and one of the other one is also equal.
okay, very nice, very nice. So that is a trivial case. So that is but obvious case if all are zeros. Okay. But if all are not zeros, then what?
So
Yes,
if
one. Yeah.
it's not,
Yes.
Instead of positive integers, we can also use natural numbers because they don't
Yes.
include
But
zero.
I am not changing, means I don't want to change positive integers whole word. Here we have to take in notice that where we have to use positive numbers or positive integers.
Okay, sir.
Ha ha ha. Okay, Srinandan wanted to say that when there are n objects to be placed in r places and n minus r is a positive integers, then at least one of the places must have equal to or more than the quotient of n by r. Okay. For that, let's take the example and then see what is happening. Now coming to this point, suppose I take say, uh, let's have one examples like say 1.2 plus 1.8 plus 4 plus 3.2. Take its average. What is the average? Come on, calculate it.
2.55.
2.55. Okay. So that is 10.2 by 4, I think so. So it comes 2.55. That is the average. So it is said that at least one of them is greater than or equal to t. So here we are getting 2 and rest are like this. Does it affect the meaning? Does it affect the meaning? Come on, let me know. Does it affect the meaning or not?
It doesn't.
Huh?
No, sir.
No, it doesn't affect. Okay. Now coming to the thing that what Sri Nandan wanted to say, when we take n objects and we have to place in r boxes or r places, then n minus r, obviously n greater than r. So n minus r is greater than 0. Then at least one of them have the equal to or more than quotient. Now remember, what is the meaning of division when we do the division? What is the meaning of division that you know? What is the meaning of division that you know? What we do? Yes, Tanish.
When you separate a certain number of objects or like anything into equal parts.
Okay. Okay. So suppose I have to subtract say 4 from 23 to get the positive remainder. Yes, some more participants have raised their hand. Ishan.
Yes. Multiple subtraction.
Okay.
Means many subtraction.
Multiple sub. Oh, good. I got your feeling. Actually, Ishan may want to say or wants to say that we should subtract the same number repeatedly from the given number. So we are subtracting here of, then there comes 19, again 4 subtracted, then 15, again 4 subtracted, then 11, again 4, then 8, sorry, 7, and again 4, then we stop at 3. Again 4 we can subtract, but the subtraction would be negative. We don't want negative. So how many times we subtracted? 1, 2, 3, 4, 5. So this long chain can be expressed in some different notation, in some different notation. And then what we get, that 4 5s are 20, remainder is 3. So what Srinandan stated, that n by r, or sorry, n by r objects minimum. So when I have 23 objects and 4 boxes, then 23 by 4 is 5 integer 3 by 4. So its integral value is 5. So one box, or at least one box, should have these objects 5 or more. More means till 23. They can't cross that number 23. I hope, Srinandan, you might have got. I think you had put in our chat. So if you want to comment on this immediately, you can speak. And if you want to ask other than these additional things, you are allowed to ask immediately. And if you have some doubt to understand, so here you can ask immediately. Now integers can be replaced, again and again it is happening. Integers can be replaced by positive numbers, and so this third version of pigeonhole principle goes with some rational and irrational numbers also. So it is not the case that we are actually distributing some objects, but we can deal with some numbers, and it can give us an immediate idea that whenever we have the average of positive integers, then we have immediate feeling or knowledge that at least one of them is greater than the average, and at least one of them is greater than the average, or both are equal to the average. So that is an immediate case. I think Tanish has raised the hand. Yes, Tanish, what you wanted to say?
Nothing. I was just gonna say that it also works with rationals and
Yeah.
irrationals.
Yes. Now 1.2, 1.8 are rationals. You can take irrationals, not to worry. And I hope many of us know what are rational and irrational numbers. If you don't, just raise the hand that I don't know what are rational and irrationals. If yes, then we shall go ahead. Or otherwise, I shall give you just a brief idea of rational and irrational. Everybody knows. Good. Going ahead. So here we have such a statement of the pigeonhole principle. It's good to see the statements. Now let's have that some questions or very simple ideas to apply our pigeonhole principles. We shall go step by step, not directly. Okay. We shall go step by step. Okay. Very simple. Among 13 persons, there are 2 born in the same month. Why? Is it correct? If yes, then support why. Yes, Tanish.
There are 12 months.
Hmm.
So just using the pigeonhole principle, we
Hmm.
know that there are 12 months. So like the 13th person must be born in the common month with the first 12 people, like one of them at least.
Good.
And
Let's
that's the worst case scenario. The best is
okay.
that everybody is born in 1 month.
Okay. Good. Okay. So many persons have raised the hand. Let's see what. Oh yes, Vanya.
Since there are 12 months and we take the worst case that one is born in each different month and like one will be left, so it'll go in a
Mhm.
month and so there will be two in one.
Okay, correct. So I hope that everybody has the same explanation because it is just simple. But formally, what we can do that 13 persons is nothing but the 13 objects and 12 months nothing but 12 boxes. So we are bringing this problem to our PHP pigeonhole principle, and we are now immediately that here when n boxes and n plus 1 objects, then our principle is immediately applied. Yes, Jay?
Yes, sir. So I wanted to say that if we want to say it in a more mathematical way, we can say that that 13 persons is our 13% is our n objects, and 12 months is our boxes. So
Hmm.
at least according to the pigeonhole principle, at least one box must have more than one. At least one month must have more than one person born in.
Correct, correct, the same. So n boxes and n plus 1 objects. So at least one box. So while applying that, no need to tell the worst case again and again. It is clear that it is the thing when there are n plus 1 objects and n boxes, then at least one box must receive more than one object. That's all. So applying PHP, 1 month should have at least two persons having their birth date in that month, and hence our statement is correct, and we had provided the reason. Let's have one another thing that second one, how many persons do you need to be sure that to be sure that two persons have the same birthday? How many persons do you need to sure that two persons have the same birthday? Okay, Shrinandan.
If you take a normal year, I'm not counting leap years. There are 365 days. So if you
Hmm.
need 365 plus one is the minimum number of people. So the answer is 366 if you don't count
Ha,
leap years. But if you count the leap years too, the answer is
ha.
367 because in leap years there are
Okay.
366 days.
So is there any another answer? Is there any another answer than this what Srinandan told? Then only keep your hands raised, or otherwise put your hands down. Okay, so everybody got that. When we have to get, suppose if it is a normal year, not a leap year, so it has 365 days. So these are the boxes. So we need n plus 1, sorry, n plus 1. So person should be n plus 1. So n boxes and n plus 1 persons. So two persons have the same birthday, sure shot. If it is a leap year, then 360 days are there for leap year, then 377 persons. Okay. Now let's come to our regular day-to-day life and say that a person may say, I have my birth date is 7. It is not necessary 7 January or 7 July or 7 August or 7 February. 7 is the birth date. So if we reshuffle or just change instead of birthday, we go for birth date, then what will happen? How many persons do you need to sure that two persons have the same birth date? Okay. And it is not now the case that whatever the month be, okay, whatever the month be, don't consider is it February or March or August, July, like that. Yes, Manas.
Yes, sir. So the most number of days in a month is 31.
Hmm.
Therefore, we will have 31 plus 1 equal to 32.
Correct. So 32 is only the correct answer here. So if there are 32 persons, then at least two of them have the same birth date. If your answer is other than 32, and don't consider the cases, if February, then that, if January, then that. No, in general, 32. If your answer is other than that, raise your hand. Okay, Srinandan. Oh no, he has put hands down. Okay. I hope that you got these things what we are solving. Okay. Now suppose let's have the next third one. Among the integers, 1, 2, 3, and so on till 200, comma, if semicolon, not comma, semicolon, if 101 integers, not 101 Dalmatians, 101 integers are chosen, then show that there are two among the chosen. There are two among the chosen such that, yes, Tanish, what happened? Tanish.
I raised by mistake.
Okay, no worry. Such that one is divisible by the other. One is divisible by the other. So write the question. Okay. Here two participants have raised hand. Yes, Srinandan.
Sir, if you take uh, out of the set from 1 to 200, there are 100 even numbers. If you take 101 integers out of them, there is a more than good chance that at least two of them are even numbers. So both of them are divisible. So there is, I think, one of them will be divisible by the other.
How can? Idea is better, no worry. But we have to support confirmly. And I hope that you got some small hitch. There is
Sir, what
happening
is
something different because, who is speaking?
Yes, sir. What is full form of
Only one
ST?
person may. Oh, ST, state transport. Sorry. Show that. Sorry, I wrote by habit ST. ST means show that. Okay.
Okay.
Srinandan, did you recognize that? Suppose one even number is 78 and another even number may be, say, 166.
They're not divisible by.
It may happen, no? So yes, but your idea, I really liked some kind of original idea. Yes, Tanish.
Sir, but like the only way to see that they're not divisible by each other is by choosing primes. But if you choose any other numbers except primes after choosing all the primes, then one of the numbers must be divisible by another one.
Okay, again, repeat what you wanted to say. I didn't get. You have used the word subprime
No, I
or not?
use only prime.
Prime. Okay. So what if suppose the chosen are not containing any prime, because I think the number of primes till 200 is not more than 50.
Yeah,
And
so if they're not primes, then they're multiples of each other, maybe, because
maybe
like
we want must be.
no, but it will be because if you pick 101 and none of them are primes, then there must be at least two numbers, like two
Mhm.
odd numbers, which are multiples of each other.
Two odd numbers.
Yeah, if you pick odd numbers, but then if you pick even numbers, then they must be a
Okay,
multiple.
but
Like if you choose even numbers, it's pretty easy to prove that they are multiples of each other. But if in odd numbers, like some odd
your
multiples
voice.
will be there.
Okay, but it is not supporting confirmly what we want to show, because we are doing some statements. It is correct that if we are choosing all odds or all evens or we are removing prime, but we are choosing them randomly. That is also a case. Yes, Swasti.
Can I modify what Tanish said a bit?
Uh-huh.
So when we try to take numbers which are not divisible by each other,
Uh,
we end up taking all the prime numbers.
huh.
But as you said, there are less than 50 prime
I
numbers.
don't know. I don't know. I just said randomly.
Okay, let's
Hmm.
assume that's true. Then,
Uh-huh.
then we have 101 numbers. Like you have chosen 101 integers.
Hmm.
So yeah, and only like some of them are prime. So others will be divisible by each other, I think.
Yeah, it is but obvious. That's right. But we have to confirm, sure shot, that our
Yeah.
choice may contain prime or may not contain prime. Then
Hmm.
what will happen? That is, and it is not necessary to consider that yes, it is containing prime or no, it is not containing prime. Without considering that, we can go. It is that we should deal with some kind of, say, even and odd and prime, because we are in integers from 1 to 200. Okay.
Yeah.
Hmm, hmm, hmm. Yeah,
I
you
got
are
a new
thinking.
answer.
Yes,
So
go ahead.
once you pick 100 integers out of 200,
Hmm,
like if you pick wait,
hmm.
yeah,
Yes.
so if you pick 100 integers out of 200,
Mm-hmm.
then like I don't know how to explain, but
Mm-hmm.
um
To try at your no worry. See, if you
or
are correct or incorrect, that is not a big question. You are trying, that is a big part that we want.
okay, so I think it is possible
Yeah, it is possible that we have to show
that
that. Ah,
yeah, so uh, they're definitely less than 100 primes.
yes.
So after we pick all the primes, there'll be some numbers left before we reach 100.
Hmm.
So prime numbers are the only numbers which are not multiple of other numbers. But then if we pick more numbers than primes, then it'll be
Mm-hmm.
a multiple of it'll be a multiple of any one of the primes which we have already chosen. But if we don't choose primes at all, then uh, then like there must be at least two even numbers,
Mm-hmm.
and there'll
Okay.
be multiples of each other.
Okay. I think somebody has raised the hand here. Yeah, Pragyan. Pragyan has
No, sir,
raised the
I
hand.
raised it by mistake.
Okay, okay. Not to worry. So you are trying very well. Okay. Now remember that here we have 1, 2, 3, and so on till 200. These are 200 positive integers. Or first 200 positive integers. Okay. Therefore, there are 101 from them can be expressed. Yes, Vihan.
Maybe we can find the evens and the boxes. Suppose if 200 are the positive integers, it can be the
Mhm.
number of n. They can be 101 can be the boxes.
Mhm. Go ahead. I think you are not quite audible for me.
Sir, I
Did
think I
anyone
just
repeat
have a
what
small idea.
did he say? Uh-huh.
Sir, so we have 200 positive integers from which we are choosing 101 integers.
Uh-huh.
So those 200 integers, we know 100 of them will be odd and the other 100 will be even.
Hmm.
So we can say in the worst case scenario, all the 100 integers of the 101 integers might be odd or even, and there will be a rest one integer. So in the worst case scenario, there might be 100 even integers and one odd integer, or 100 odd integers and one
Mm-hmm.
even integer.
Okay. Okay. Can be.
Sir,
Yes, Pragyan.
yes, sir. So
Huh.
I have a few facts, sir. So like we can't choose one, nor can
Uh-huh.
we choose two, because if we choose one, then like every number will be divisible by the other, and like
Huh.
if we choose two, then you can't use even numbers. So that leaves us
Mm-hmm.
ones, but like the odd numbers also sometimes they might repeat. Sir, so I
Hmm.
think we can start by taking 101, because 101 into 2, like dividing it with 2,
Hmm.
multiplying it with 2, we get 202 at the minimum. So then all the numbers above it, they
Correct.
don't come below 200. So like
Hmm.
numbers from 101 to 200 are 100. Yeah, there are 100
Okay.
numbers.
Okay. Mm-hmm.
And then uh, then I don't know which number shall I choose, because we get 100, and
Oh.
what can be the
Hmm.
101th number?
Okay, but your idea is very nice. One is but obvious if we include one. If we include two, then automatically at least one of the 101 would come like that. Even good. Okay, so you are having ideas. Somebody has put. Okay, Srinandan have got some idea to do with PP3, PHP3. Okay. That's nice. That I think Tanish also wants to say something again. Yes, Tanish, you have raised the hand.
Yeah, I wanted to say that like I got a few
Your voice is
ideas.
breaking. Either my internet or your internet has problem. I don't know.
Now can you
Is
hear
he
me?
audible properly?
Yes.
Ah,
Yes, yes.
ha, ha.
So I was saying that I have some ideas, but I don't think I got the solution yet. My ideas is that like you can't ever choose one. Otherwise, like two of them will be multiples of each other for sure. And then you
Yes.
can't choose two because after you choose all the odd numbers, you have to choose one even number.
Mm.
So and also I think that
Mm.
you can't really choose like
Mm.
like you can't choose more than or like at least you have to choose some prime numbers. That's what I think.
Okay. Okay. So that's nice to see that you are developing. Okay, Pragyan got answer. Yes, Pragyan.
Sir, so like I said before, sir, we get 101 to 200. So those are
Mm-hmm.
100 numbers. So another number, it can be like 99,
Huh.
and the least number
Mm.
is, I think, 67. So any number between 67 to 100
Huh.
we can choose it, I guess. Because like 67
Okay.
into
Okay.
3 is 201.
Huh.
No, I
Okay.
not also
Nice try, but
63,
very
sir.
good. Yeah, we can take
Because
four
then
also.
we'll
No
get
worries.
like two numbers.
Hmm. Okay. Yes. Swasti. She wants to say something.
Yes, I think I got the answer. Can I tell it?
Yes.
So if we choose all the numbers from 101 to 200, then none of the numbers will be like divisible by the other.
Mm-hmm.
So and then, but they are only 100 numbers. So we need to choose one more number, and that should be so.
Hmm.
We can choose any one which is less than 101. And so if let's say we choose
Hmm.
99, and 99 into 2 will be in 101 to 200.
Mm-hmm. 99 into
2.
2 is 198. Hmm.
Yeah. So and that is
Hmm.
from 101 to 200. So if we choose any number from which is less than 101, it
Hmm.
like a number between 101 and 200 will be divisible by that number.
Okay. But suppose if I take some 50 from here and 50 from there, then there will be something like that.
No, I don't think so because this is the worst case.
Mm-hmm.
Sir, I
Ah.
think like it is confirmed that we need to choose 101 and 200, all the
Hmm.
numbers between them.
Hmm.
And the extra number, we can choose them from between 67 and 100.
Mm-hmm.
Any one number, because that times 3, that times 2
Okay.
gives us one multiple, and that times 3, like 67 times 3 will give us 201.
Mm-hmm.
So like it can't repeat itself.
Okay, but it is not said that which numbers to choose. It is said that any 101 numbers are chosen. So don't make the problem that we have to choose this and that. We are choosing 101 randomly. Remember very well. We have chosen 101 randomly. So out of 200, whenever we choose 101, then it is always that we have at least one pair, that two among the chosen, that one divisible by the other. It's okay. In that case, if you say that if we are choosing one in the our given 101 integers, then automatically the theorem is done or the problem is done. If the chosen 101 integers contain 2 and rest 100 would be all odd, and then therefore we can't work immediately. Why? Because here when all odd comes, then there's something divisible by all and other. So instead of doing such groups, we now have to think to derive or arrive the final conclusion in general. But initially what we are thinking in our mind that yes, when one is chosen, the problem is over. If two is chosen and other rest all are odd, then among the odd, one is the multiple of the other, or one is divisible by the other. That is again evenly proved. Then next cases, if you go on increasing, then there would be many complications. So what can we do? That yes, Sai Charan, you want to say something?
Sir,
Hmm.
sorry for interrupting, but are you
Huh.
writing something on there?
No, I am not writing. I am not writing. Huh?
Okay.
Okay. Yeah, I am just speaking. So what I wrote here that there are 101 numbers. Actually, I only wrote 101. Here I should say 101 integers. Okay, from them can be expressed as, say, we can say that ni is equal to 2 raised to say something ki into ai. Okay, now 2 into something. Now ki is nothing but here some kind of integer. Say here ki is a natural number. Oh no, is a non-negative integer, not natural number. Huh? So what we have that a 101 integers I said can be expressed as 2 raised to something, 2 to the power something into ai, and I said 101. How? Yes, Sai Charan?
Sir, I don't understand ni equals 2 per ki.
Yes, I am coming to that point. Here, what is I? I stands for 1, 2, 3, and so on till 101. These are the order numbers. These are not our positive integers, what we intend to choose. That is order number. So n1 can be 2 raised to something into ai. And ai is again a positive integer. That is a natural number. ai belongs to natural number. And I goes from 1 to 101. Ki is our non-negative integer. So they are multiple of 2. And I wrote that there are 101 multiples of 2. Do you agree with this statement? We have 1 to 200 numbers, integers, positive integers. And I am claiming that among them, there are, uh, that should be, I am writing properly. Therefore, there are 101 integers. From them can be expressed as power of 2 into some natural number. 101 integers, I said. How? Explain me.
Sir, are you asking how you to? Sir, can you repeat the question? The last
Question
one.
is, I said 101 integers which can be expressed as 2 to the power something into natural number. And we are given with only 1 to 200 integers.
Sir, I think it is because there are 101 even numbers.
101 even numbers. How?
Sir, if you take, just look at the list.
Yes, you count. Others also count. And let me know, are there 101 even numbers?
There are
Come on.
100.
Yeah, there's 100, sir.
Oh, 100. And I wrote
Odd numbers
101.
are 101.
Yeah, odd number.
Yeah. No, no, Tanish, you are not audible properly, for me at least. Tanish, can you repeat
Yes,
what did
sir.
you say?
I was just saying that there
Ah,
are 101 odd numbers and 100 even
sure.
numbers.
But there are total only 200 numbers. If 101
So
odd
both
and
should be
100,
100.
that should be 100. Okay, now let's clarify the thing. Here I stated that 2 to the power ki into ai. Ai is a natural number, sorry. Ai is a natural number and I is from 1 to 101. And ki is a non-negative. Non-negative integer starts from 0, 1, 2, and so on. So if there comes 2 to the power 0 into 1, which is equal to 1, so and after all the next, when I take 2 to the power 1, then we have all. Okay, means what? Whatever the number, here I can take here 2 raised to 0 into 3 also. Yes, that is also the case. And so 101 integers, if I consider that I have to take only even with 1, then there come what? Then there comes all 101 integers. So I intend to write like this, that 101 integers chosen among these are written as like this. Means what is the case? They are either even or odd. If they are odd, then ki would be 0. If they are even, then ki would be something. Now let me know, did you agree with this or not? Did you understand the case? 101 integers we have chosen. Among them, what is happening? Any one of them, either even or odd, it is immaterial because ki is non-negative. So if it is purely odd, then ki would be 0. I hope everyone agreed with this. And we can say that therefore ai is the greatest odd divisor, greatest odd divisor of ni, which is from 1, 3, 5, 7, 9 till 199. Now try to recollect the meaning of this. What? We have taken 101 integers and those can be expressed as 2 to the power ki into ai, where ki is a non-negative integer. Okay, and I from 1 to 101. Okay, then ai is the greatest odd divisor. If that number is purely odd, then 2 to the power ki would be 1, and so ai itself is the greatest odd divisor of ni. If it is an even, then that ai would be the, like say 12. If there comes 12, then 12 can be expressed as 2 square into 3. Then 3 would be the greatest. Then 3 would be the greatest divisor of 12, the greatest odd divisor of 12, like that. And that ni comes from, and that ni comes from 1 to 199. Okay, so there are how many, which is from 1 3, that is ni is nothing but the product of 2 to the power ki into ai is the greatest order divisor of ni, which is from 1359. That is what ai takes 100 or AI is one of the 100 numbers 1357 till 199. Okay. Now what? Therefore, among chosen 101 Ni, because I from 1 to 101, so Ni are 101 numbers that Ni. So among these chosen 101 numbers, that is our chosen number is in short Ni. I stands for 1 to 100. That at least, yes, Pragyan, what you want to say?
Sir, sir, so you are telling that AI is the greatest like divisor of 101.
Huh?
Sir, so
No, 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 no,
101.
no. No, I is the subscribe over there that shows the order A1, A2, A3, A4 like that. It is not necessarily that if I say A2, then A2 should be 4 or sorry 3 or 5 or 7 or 9. That is just our means. See there, I want 101 literal terms, and I have only 26 literal terms in English. I may include some Greek and Hebrew and all. Why? So I can have like A1, A2, A3, and so on. So similarly here that AI is taken. So that is
Okay, sir, got it.
1 to 101, not from our among 200. That is the case. Yes, Srinandan, what you want to say?
So based on what you said, I think if you any odd number can be expressed as some other odd number multiplied by 2 raised to some power,
Uh,
and in that the numbers that are left out,
uh,
that are not the last number, if it's an even, if it's a multiple of 2,
uh-huh,
not if, yeah, it's an even number and you multiply it with an odd number, the one
uh,
from the list,
uh.
you're bound to get a number, another number in the list.
Okay. So here what we have played a typical role that we have chosen 101 integers like this form, that 2 to the power ki into AI. Okay. And AI is the odd part of that. So AI is the greatest odd divisor, which comes among from 1357 till 199. Okay, whatever it be. Then among chosen 101 numbers from that is Ni. Whatever Ni, 101. There are N1, N2, N3 till N101. We are choosing any two of them. So among chosen 101 numbers Ni, at least two have equal odd parts after removing 2 to the power ki, because there are only 100 odds. Remember very well. There are only 100 odds. And in that expression of Ni, AI is the greatest odd part or odd divisor of Ni. Therefore, being 100 only odd, we have any two odd parts are equal after removing 2 to the power ki. Did you get till here? Yes, Sai Charan.
Sir, I did not understand
Hmm. What?
this now.
See, whatever the numbers we had taken, say randomly, I shall say here that above I am writing, say I had chosen, not necessarily. I have chosen 3, 5, 8, then say 10, then 13, then 18, like that. So 3 can be expressed as 2 raised to 0 into 3, then 2 raised to 0 into 5, then 2 cube into 1, then 2 raised to 1 into 5 raised to 1, or only 5 here. Okay. Then if I have next is 50, suppose. Then 13. 13 adds 2 raised to 0 into 13. 18 adds 2 into 9. 50 adds 2 raised to 1 into 25, like this. So the odd parts, these are the odd parts coming. Those are our AI. Those AI are only 100, and we had taken 101 numbers. So by PHP, actually here I should write by PHP. By PHP, those chosen 101 numbers, there should be at least two having equal odd parts. Now, have you cleared? If you have problem, raise the hand.
No doubt is solved, sir.
Yes. Now what? So typically, when then typically we can say that, say I am writing here only, then typically we may have, suppose, uh, NP is nothing but 2 raised to P AP, and NQ is nothing but here 2 raised to Q and AP, that these odd parts are equal. Okay, so there exist at least two. Now you agreed with this. So these two existing are these NP and NQ. P and Q are the subscribes, that is 1 to 101, whatever the numbers. These odd parts are equal, then it is clear that if P greater than Q, then NP will be divided by NQ. And vice versa. If Q is less, the Q is greater than P, or P is less than Q, then NQ is divisible by NP. So our problem is completed. Did you get the final conclusion? Who didn't get, just raise the hand. Everybody got. Yes, Tanish, what happened?
I don't understand what is NP and the last
NI,
part.
NI is any our number chosen 101 integers. So I don't know which two NI have equal odd parts. So I considered P and Q. Okay, I
Okay.
consider P and Q. So their odd parts are equal, AP, and then therefore
Yes.
2 raised to P, 2 raised to Q should be different. Why? Because they are different numbers. Then
Yes.
it must be that as 2 raised to P the same. So either P greater than Q, then NP is divisible by NQ.
Yeah.
And
Got it.
if Q is greater than P, then NQ is divisible by NP. So problem is completed. Got all?
Yes.
So I think it is time to say bye-bye. Oh, we are running late. Maybe Onkar sir, is time over?
Yes, 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 yes.
Okay, so it is time to say bye-bye and good day. See you tomorrow.
Hi,
Sir,
sir. Thank you.
just
Bye,
one
Yes,
sir.
minute.
Thank you, sir. Have a
wait,
good
listen,
day.
Thank you.
Is
listen.
there any homework for students?
No, I shall put in evening, because I think Thomas sir has, George sir has given homework. Then I am not going to trouble them on very first day.
Okay,
So
okay,
by evening, because I couldn't type, frankly speaking. So I shall send by evening. Okay. Yeah.
okay, okay.
Okay. Bye bye.
Bye.
Bye to all.
Yes, thank you,
Thank
sir.
you,
Thank
sir.
you.
Bye.
Yes. Bye bye.
Bye, sir. Thank you.
Okay. Bye bye.
Sir, will these presentation be posted in the Google Classroom?
Who is speaking?
Sai
Presentation,
Shridhara.
if required, then because it's a random write up, you will receive some better write up. Okay.
Okay.
Yeah. Okay.
So the problems answers will also be posted on the classroom, right?
Yes. 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 Yes.
Yeah.
So
Okay,
not
sir.
immediately, but after. And Pragyan, you also play tabla. You
Yes,
have
sir. I
that.
used
Okay.
to.
Very good. From which area you are?
Sir, Mumbai.
Mumbai. Okay. So there are so many better musicians. Nice. Who is your guru?
Sir, I used to play it.
Okay. No worry. Good. So chalo. Bye to all. Yes. Bye bye.